So you guys, here's what IB would like you to understand about reflection and Snell's law that we're going to talk about today, refraction and Snell's law. You should be able to describe the reflection and transmission of waves at a boundary between two media, so we'll talk about that, and state and apply Snell's law, which has to do with refraction. So that's what we're going to talk about. But before we get into that, let's review reflection a little bit. The law of reflection. What do you remember?
Angle of reflection equals the angle of incidence.
Excellent. The angle of incidence equals the angle of reflection. Super straightforward. When a beam of light hits a surface, it reflects off at the same angle. It doesn't even have to be a beam of light. It could be any type of wave. If you wanted to write this out mathematically, it would be super easy. You would love this mathematic equation. The angle of incidence equals the angle of reflection. There's no exponents, there's no multiplication, no addition, no subtraction. It's there. You got it. It's equal. The thing that you need to remember is how we measure those angles. What do we measure those angles relative to? Relative to the normal. Okay, so when you're drawing a ray, those angles are measured relative to the normal. So here's my surface. Here's a ray of light coming in. The angle of incidence is here. And that might seem kind of strange, but you might remember that when we draw a ray, remember that's just representing a bunch of wave fronts. The wave fronts are perpendicular to the ray. And so if we measure the angle that the ray makes with the normal, that's exactly the same as the angle that the wave front makes with the surface. So that's kind of why we do it that way. Okay? We don't usually draw a whole bunch of wave fronts. We're going to talk about regular versus diffuse reflection just a little bit here. So let's get to that. Here's what the law of reflection looks like. Okay, incident ray, reflected ray, those angles should be equal. It's all pretty straightforward. Everything good? Okay. This is the difference between regular and diffuse reflection. Light reflects off of most substances. This is how you see things, right? I mean, either something makes its own light, like a flame or a light bulb or a star, or light reflects off of the object and you can see it that way. The question is, why can you sometimes see yourself in an object? When you sit in front of a mirror, why can you see yourself in the mirror, but when you stand in front of this wall, you can't see yourself in the wall?
Because if it's regular, it'll all be
So yeah, notice on this right-hand drawing, on the diagram B there, the rays of light that come in when they hit the surface, if the surface is smooth enough, they all bounce off and they're still parallel. They're all still in the same direction relative to one another. And that's the kind of situation where you'll see an image. Surface A is more like a wall or just about anything else, where it's rough enough that when parallel light rays hit it, they bounce off in all different directions. Each individual light ray is still bouncing off at the same angle that it hits. It's just that the surface is at a different angle for every single one. You won't see an image in that kind of a surface.
So if you made like something with these,
so it's just a diagram. We're not going to get into optics a whole lot. I did ask you in that homework assignment if you're interested, to read the section about curved mirrors and things like that. That's more if we were to study optics in more detail. This picture gives you a little bit of an idea of how we see images in mirrors. So notice we have our little green soap bottle down here, and light is bouncing off of this soap bottle and going in all directions. What's the key reason you know that light is bouncing off in all directions from this bottle?
Because you can see the whole bottle.
You can see the whole bottle. What about if you move around it? Will the bottle will you still be able to see it?
Yeah.
That lets you know that light's going in all directions. If it was only going in one direction, then if you walked around to the other side, it would disappear. Yeah, it'd be dark or something like it. You wouldn't see it, which is kind of weird. That doesn't usually happen. So light hits objects, tends to reflect off in all directions. Some of that light goes straight into your eyeball, and you look down and you go, oh, look, there's the shampoo bottle. Okay, but some of that light might hit a mirrored surface like this and bounce off and go into your eye. Your brain doesn't know that the light changed directions. Your brain thinks that light travels in straight lines. So your brain goes, where did these two rays of light come from? And it takes them all the way back to where they met, and that is where you see the shampoo bottle. So that's where the image will be. And this is why when you look into a flat mirror, the images you see are behind the mirror or within the mirror, okay? Because that's where it looks like the light's coming from those objects. The distance to the image should be the same as the distance to the object. The distance that the image is behind the mirror is the same as the distance to the object in front of the mirror, okay? That's kind of the lab we did last class. All right, so you're having a nice romantic evening with your honey pie out there, you know, on the lake shore, and the moon's out. Why does the moon, the sun or moon, why does the light look like a column rather than something else? Okay, so if you've got all these ripples, you can have light coming from the moon at all these different angles, and it ends up creating a long column rather than a nice little disc, you know? That's all because of reflection. Okay, let's talk about our main subject for the day, which is refraction. Who remembers what refraction of light is? How can you describe refraction of light? Excellent. So that's what we're looking for. So refraction is when a wave, okay, and in this case light is what we're talking about, when it changes direction due to a change in velocity upon entering a new medium. So that's what refraction is, okay? We're going to get into more details of that today and how to calculate things like that. So here's the situation when a light ray hits the boundary between two materials. So this picture on the left, we've got it coming from air into water. When a wave hits a boundary, what happens to that wave? What does it do?
Some of it reflects and some of it refracts.
Excellent. Some of the energy reflects off. Some of the energy is transmitted into the new medium. Just like with the slinkies. Remember with the slinkies, you send a pulse down, the reflected wave was always smaller because some of that energy was transmitted, right? Same thing with light. Some of the energy reflects off, and the angle of incidence is the angle of reflection. That's super easy. And then some of it bends and enters the new medium. Now, it happens the other way around, too. If I was underwater, like in picture B here, shining the light towards the surface, some of that energy would reflect back down. Some of it would refract out into the new medium. Okay? Notice that when I'm going from air to water, the light ray bends towards the normal. When I'm going from water to air, it bends away from the normal. So, in which material does light travel faster?
Air.
Does that seem obvious to you guys? Make sense? And do you guys remember when we explained that? So you guys are all in agreement that light travels faster in air than it does in water?
Yeah.
And do you guys remember the whole wheel with the axle with the two wheels analogy, right? The whole thing? Great. And that is true. So how about this one? This is a term we don't use a lot, but sometimes some books use it and sometimes you'll hear it. Which material is more optically dense then, do you think? Yeah. Yeah, water will be more optically dense. A material that's more optically dense, light travels more slowly through it than it does through other materials. So that's some terminology there that might come up. Notice also that if I have a material with two parallel sides, like let's say a piece of glass and both sides are parallel, here I have light traveling in, it refracts towards the normal when it enters the glass, it refracts away from the normal when it leaves the glass. What's true about the ray of light in the air going in and the ray of light in the air going out? Angle's the same. So how do they relate to one another, those two rays?
They're parallel, but they're just
So,
offset.
excellent. So they'll be parallel but offset. This because of the refraction in the glass, right? So here you are, you know, looking through a window, thinking that you see something here, like, you know, I don't know, a nugget of gold or whatever, and that's not where it is. It's really over here.
But if you look like straight,
If you look straight through, yeah, because it doesn't refract. So this is why when you start looking at angles through windows and through glass, things start to look kind of weird, right?
it's like when you look at
Oh, yeah, I know it's been snowing lately, but what if it was a nice hot summer day and you decided you wanted to go buy yourself a bottle of Coca-Cola? Then you go and buy your bottle of Coca-Cola and you're all happy and excited, but you don't realize that they're ripping you off. Coca-Cola Corporation, biggest company in the whole world, maybe. I don't know if it is, but not. But you know what I mean? They are ripping you off because that's all the Coke you're actually getting. You think you're getting a full bottle of Coke, but no, you're actually getting a partial bottle of Coke and a lot of glass that you can't tell because of refraction. The way the light bends when it comes out of the bottle deceives you and makes you think that it's Full. Oh yeah, that's totally real. Totally real. Here is what we're really here to talk about today. Snell's law, discovered by the famous scientist Willibrord Snell. Can't remember what country he came from, but I think he's just got an awesome name. Willibrord. I should have named my kid Willibrord. Maybe. Okay, so he started investigating refraction. And he recognized that the angle of incidence does not equal the angle of refraction. It does equal the angle of reflection, but refraction is different. And he looked at all these relationships, and he finally found one. And the one relationship that he discovered is that if he took the sine of the angle of incidence, divided it by the sine of the angle of refraction, he would get a constant value, a number that was the same no matter what the angles were. He chose a new angle of incidence, he'd get a new angle of refraction, and the ratio of the sines of those angles was always the same for a given material. This is pretty interesting, and he was always testing it from air into that given material. So he gave this, I don't know if he's the one that gave the name to it, but we talk about the index of refraction of a material, and that's what that constant is. It tells you something about the speed of light in the material, how much it refracts. It's called the index of refraction. There's a more general version of his law, which is there, the second line now, and this is what's written in your IB data booklet. This is how they do it. And I don't really like it this way, but that's the way it is. But ultimately, what he discovered more generally was this: the index of refraction of one material times the sine of the angle in that material equals the index of refraction in the second material times the sine, I'm running out of board, of the angle of that second material, okay? So that's how IB gets to this whole relationship right here. It turns out that if I look at the ratio of the indices of refraction, that will equal the ratio of the sines of the angles, but the angles, notice they're opposite in this case. I have index 1 over index 2 equals sine of 2 over sine of 1, so they're flipped. And that also tells me something about the speed of light in those materials. That's what the V's are about, V2 and V1.
Wait, so that constant is the index of refraction?
The letter N is the index of refraction, and it will be a constant for a given material.
What does anything do?
It is an index of refraction. The index of refraction of a vacuum, of empty space, the index of refraction is 1. Air is basically the same as a vacuum. It's slightly different. It's got an index of refraction of 1.0003, but for most of our calculations, we can just use 1 for air. Water has an index of refraction of 1.33. Okay. You probably don't need to memorize water, but you should know that vacuum has an index of refraction of 1. All other materials that light travels through should have an index of refraction greater than 1. So here are some indices of refraction for some different materials. You don't need to memorize these. You probably don't even need to write them down, but just so you can see, vacuum is 1, air is a little bit more, water is 1.3, glass is usually about 1.5. Different types of glass have different indices. Plexiglass, sodium chloride, diamond 2.42. Diamond has a really high index of refraction. It's one of the reasons why diamonds are so appealing, and one of the reasons we can make them sparkle so nicely. So notice also that the index of refraction of a material, you don't have this equation in your data booklet, but that's what those two velocity ratios in your data booklet were about. It's the speed of light in a vacuum divided by the speed of light in that substance. That's what the index of refraction is. So that's why you can't have an index of refraction less than 1, because then you'd have light traveling faster than the speed of light, which, according to relativity, is impossible. So please remember that the index of refraction of material tells you something about the speed of light in that material. It's easy to prove, and I'm not going to go through the proof right now, but you can do some basic geometry. And if you want to, you can look this up in your book. But basic geometry, looking at how rays move into a new material and doing similar triangles of these two similar triangles, you can discover that the index of refraction basically is telling you about the speed of light in that material. So you get the sine of angle 1 over sine angle 2 is the velocity in material 1 divided by the velocity in material 2. Okay? And that's in your data booklet right there. The one thing they add in your data booklet is that is also the index of refraction of the second material over the index of refraction of the first material. That's all in the data booklet. Okay, so here we have a ray of light going from air to water at an angle of incidence of 43 degrees. Please calculate the angle of refraction.
Did we ever go over this at one point?
So it appears that the answer is 31 degrees. For those of you at home, trying this at home. Okay, next slide. Now we're going to try another one. But in this instance, we've got the ray of light going from water into air. So we're just going the opposite direction. We still have the same indices of refraction. Here's our angle of incidence, 48.753466663 degrees. Please calculate the angle of refraction as that light ray leaves the water and goes into the air.
Just really, just make an intro. Straight to the side. Yeah.
Okay?
Because it's from normal.
So hopefully you guys are getting the answer of 90 degrees for the angle of refraction. So what does that mean? The light ray comes out of the water,
It goes like
and if it's an angle of 90 degrees, where does that light ray go?
the side. Parallel to the water.
Parallel to the water.
So you can't see.
It doesn't leave the water. It goes parallel to the surface. Okay? This is an important thing. So here's what we just calculated. Notice that if I'm in the water and I shine a light out, it hits the surface and it refracts away from the normal. As I make my angle of refraction larger, my angle of incidence larger, my angle of refraction also gets larger. And at some angle, which is known as the critical angle, the critical angle is the angle of incidence at which the refracted ray is 90 degrees. It runs right along the surface. It doesn't leave anymore. And if I go at anything larger than that angle, all of the energy reflects, and we have what's called total internal reflection. The light stays trapped inside. It changes for different mediums, okay? Is it possible to get total internal reflection if the light was going from air into water? Is it?
No, because it's
Great. In order to get total internal reflection, the light has to bend away from the normal. So you always have to be going from a more dense into a less dense material for it to work. It doesn't work the other way around. Okay? So the critical angle in total internal reflection, the critical angle of incidence is the angle at which the angle of refraction is 90 degrees. Okay? Anything beyond that critical angle and you get what's called total internal reflection. Is when the critical angle is exceeded. Okay? And again, notice that you can only get this happening when you go from a more dense to a less dense material. Okay, here's a question for you to ponder and vote on. You want to see your whole body in the mirror, from your feet to your head, all at the same time. How big does the mirror be? How big does the mirror need to be? How big does it need to be? Think about it, talk about it, we'll take a vote. So here's our voting results for class. I think it's probably more than 9, but some of you didn't vote. This is one of those unfortunate situations where nobody's right. Oh, sorry, guys. B is the correct answer. B is the correct answer. Has to be half your height. Think about the geometric optics that are going on here. The light coming from your toe has to hit the mirror and make it to your eyeball. In order for it to do that, same thing from the top of your head. In order for it to do that, the mirror has to be half your height. Okay. If you move farther away, you would think you could see more of yourself, and people often mistakenly think that. And we'll test it here in a second. It's not true. No matter how far away, you'll see the same amount of your body in the mirror, regardless of how far away you are.